Okay, welcome everybody to today's meeting of the CUNY Set Theory Seminar. We are very pleased to once again have William Chan of Carnegie Mellon University speaking to us, and he will present the second in his series of 2 lectures on determinacy and partition properties. Okay, William, take it away.
Thank you. Thanks for having me back again and for coming back again. Last time we talked about we surveyed the partition properties and some consequences of partition properties from more of a purely combinatorial point of view. So in this talk, we'll be working in AD the entire time, and we'll be answering this question of Goldberg, which roughly asked what is the relation between the ultra power, the first uncountable strong partition cardinal by partition measure with respect to the second strong partition cardinal, omega sub omega plus 1. I guess Gabriel's actually here, but as far as I remember, I actually heard this question secondhand from Steve Jackson back in 2017. So this is what his question has since turned into. Okay, so what we'll show is that when epsilon is less than omega 1, the ultra power of omega 1 by the epsilon dimensional partition measure, I'll review this in a moment, is strictly less than omega sub omega plus 1. And in fact, the ultra power of omega sub omega plus 1 by the short epsilon partition measures is actually omega sub omega plus 1. So omega sub omega plus 1 is a fixed point of these short partition measures. And we'll also show that the ultra power of omega 1 by the strong partition measure on omega 1 is strictly less than omega sub omega plus 1. But I don't know if it's a closure point of the strong partition measure. Okay, so let me just review a little bit from last time. So the type of partition properties that we're looking at are the so-called correct type partition properties. So kappa arrow star kappa epsilon sub gamma asserts that for every partition of kappa the epsilon of the correct type into gamma many pieces, there is a club subset of kappa and a delta less than gamma, so that for every function from epsilon into the club, it lands into the delta piece of the partition. And on these partition spaces, we can define these filtered mu sub kappa sub epsilon on kappa to the epsilon of the correct type by saying that X belongs to this filter if and only if there is a club C, so that every epsilon function into C is a subset of the set X. And we saw last time that assuming suitable partition relations, these filters are ultra filters and even kappa complete. So let me review what would be most important strong partition cardinal that we'll be concerned with in this talk. So Martin showed that omega 1 is even a very strong partition cardinal, and in fact, so this will imply that the mu omega 1 sub epsilon for every single epsilon less than or equal to omega 1 are countably complete ultra filters. And from now on, I'll drop the superscript omega 1. Whenever I write mu epsilon, we'll refer to the epsilon dimensional partition measure in omega 1. So delta 1n is the supremum of the length of the delta 1n definable pre-well orderings on R. And Jackson showed that all the odd projective ordinals are strong partition cardinals. And for us, we will have that under AD and DCR that delta 1,1 is omega 1, the first strong partition cardinal, and delta 1,3 will be omega sub omega plus 1, which is the second strong partition cardinal. So this is how we will attack this ultra power question by considering omega sub omega plus 1 as delta 1,3. Also from last time, we saw that Martin showed if you have any strong partition cardinal and any measure mu on kappa, so that somehow you know the ultra power by kappa by mu is a well ordering, then the ultra power actually has to be a cardinal. And if you measure with normal, it's even a regular cardinal. And so you can show that this the ultra power of omega-1 by the finite dimensional partition measures always are well ordering, even without assuming dependent choice. And so therefore, Martin and Paris were able to conclude that the ultra power of omega-1 by mu1, the club measure in omega-1, is omega-2. And more generally, that the ultra power of omega-1 by the n-dimensional partition measure on omega-1 is omega sub n plus 1. So these ultra power representations of the first few cardinals are important for establishing combinatorial properties of the cardinals below omega sub omega. For instance, this is how they show omega-2 is a weak partition cardinal. It's how you show that all the omega n for n greater than or equal to 2 have cofinality omega-2, and other combinatorial properties like the Janssen property and so on. Okay, so the Martin-Paris result tells us what the ultra power by the finite partition measures are. So it's natural enough to ask, what about the ultra power of omega-1 by the other epsilon dimensional partition measures for the other epsilons less than or equal to omega-1? For instance, one thing you could start off by asking is whether these things are actually well-founded, but that's a minor concern because we just add dependent choice to get that to happen. Okay, and we saw that the finite dimensional partition measures represent all the ordinals less than omega sub omega. Now, omega sub omega plus 1, the next cardinal after that, is the next strong partition cardinal. So it's kind of interesting to ask, where do these other these other ultra powers land? So first note that when epsilon is greater than or equal to omega, these filters are not on well orderable sets. So you can't apply the Martin result from before to conclude that these things are even cardinals anymore. And certainly there are no cardinals between omega sub omega and omega sub omega plus 1. So it's kind of a natural guess to say that that the next strong partition cardinal delta 1,3 might be sort of a boundary on how far these ultra powers on these partition ultra powers on omega-1 can get. So we formalize Goldberg's question by asking, for all epsilon less than or equal to omega-1, is the ultra power of omega-1 by the epsilon partition measure strictly less than delta 1,3, which is omega sub omega plus 1? So one kind of motivation is that, so we saw that the ultra power representation for the cardinals below omega sub omega are very useful for addressing certain combinatorial questions. Combinatorics at delta 1,3 under AD is actually very challenging because most of it passes through this technical description analysis of Jackson. And if for some reason the ultra power of omega-1 by the strong partition measure was delta 1,3, it would seem to suggest like a new way to approach combinatorics on delta 1,3. But we'll show later on, unfortunately, that this ultra power is not delta 1,3. Okay, so how would you even attempt to produce these upper bound results? So these bounds come from bounds on well-founded relations which have a certain tree type representation. So the Kuhn-Martin theorem states that if you have a relation R cross R, which is delta Suslin and well-founded, so delta Suslin means you're the projection of a tree on omega cross delta, then the rank of this well-founded relation it must be strictly less than the successor of delta. Under AD, Martin showed that sigma 1,3 sets are omega sub omega Suslin, and Moshkavakis showed that sigma 1,4 sets are delta 1,3 omega sub omega plus 1 Suslin. Therefore, if you have a well-founded sigma 1,3 relation, its rank must be strictly less than omega sub omega plus 1. And if you have a well-founded sigma 1,4 relation, its rank must be less than omega sub omega plus 2. So in order to show that our ultra power is strictly less than delta 1,3, we just need to code the ultra power by a sigma 1,3 well-founded relation on R. So that's kind of our attempt. And just from seeing this, you will see that you can kind of imagine the type of techniques that we'll have to do and the complexity calculation. So I'll try my best to kind of emphasize the main idea and not get lost in these complexity calculations. Okay, so we have to start coding all the relevant objects by reals. So if you have a real z, we'll let L sub z be some standard way of coding Lipschitz continuous functions. So note that Lipschitz continuous functions are related to determinacy because every winning strategy on omega kind of induces a Lipschitz continuous function. So we'll say that a real z belongs to club code, though the intention is to code a club subset of omega 1, if and only if it has the property that whenever you're given an element of woe, so woe is the standard pi11 complete set of reals coding well orderings on the natural numbers. The Lipschitz function coded by z applied to w will also be coding a well ordering, and it'll code a well ordering whose order type is strictly bigger than the well ordering w that you gave me. So it always codes a strictly bigger ordinal. You can check that club code is the pi12 set of reals. For every element of club code, there's a naturally associated club subset. So it's more or less the kind of closure point of the z Lipschitz function. In other words, it's a set of eta so that whenever you give me a well ordering of order type less than eta, applying the LZ to that ordering gives me a well ordering whose order type is still less than eta. The important point is that using this little game of Solivay, you can actually show that for every club subset of omega 1, there is some real z, so that CZ is a subclub of C. So this method codes at least enough club subsets of omega 1. Okay, so now, in order to prove the strong partition property, you need to be able to code a function from the ordinal to the ordinal by reals. Martin came up with, but the coding system also has to have certain definability conditions that allow you to do boundedness arguments. So Martin defined a good coding system for functions from epsilon into omega 1. So it consists of the point class pi11, a function decode, which takes a real and gives you a subset of epsilon cross omega 1 with the property that whenever you have a function from epsilon into omega 1, there is a real x, so that decode x is the graph of f. And we'll frequently confuse the graph of f with f itself. There are these collections of Borel sets, GC beta gamma, whose intention is to say that if X belongs to GC beta gamma, then decode X has successfully coded a function defined at beta taking value gamma. So this is actually an important point. If you try to code a total function, it will be too complicated to do the necessary boundedness argument. And condition 3 is the most important boundedness condition. So fix a beta less than epsilon. Let GC beta be the union of gamma less than omega 1 GC beta gamma. So in other words, an element belongs to GC beta if it codes a function that is defined at beta taking some countable value. Now, if you have a subset of GC beta, which is sigma 1, 1, then there is a delta less than omega 1, so that for every element of A, the output of beta on any element of A can't exceed delta. Now let GC be the intersection over all beta less than epsilon of GC beta. So GC is what we'll call the collection of good codes, because whenever you're an element of GC, you actually code a total function from epsilon into omega 1. Okay, so this is a good coding system. When epsilon is less than omega 1, Martin showed that there is a good coding system for function from epsilon into omega 1, so that it renders the collection of good code to be a pi11 set of reals. For epsilon less than omega 1, the good coding system is actually the kind of obvious natural thing that you would do. Fix a well-ordering of the ordinal epsilon, and then use the bijection that this well-ordering gives you to code the values of the function into sections of this real, of some real. Okay, but it's more challenging to show that there is a good coding system for full-length functions from omega 1 into omega 1. And you can show that the collection of good codes for any such good coding system must be pi12, and in fact, pi12 complete. So Martin's original way of creating this good coding system involves using sharps of reals or certain countable iterable inner models. The simplest proof is probably due to Kekris that uses certain category arguments and generic coding functions. Jackson came up with a good coding system using Kunin's analysis of measures. And the last one is the only known, the last one is more suitable for generalization to establishing the strong partition property for the higher odd projective ordinals. Okay. So the following result of Martin is essentially the, I guess, the only known method for establishing the strong partition property under any context. So Martin showed that if you have a good coding system for functions from omega times epsilon into omega 1, then you can get the exponent epsilon correct type partition relations. So let me just say some brief words about how Martin proved this result. So if you have a function from omega times epsilon into omega 1, so think of these as epsilon many blocks of omega. Let block of f be a function from epsilon into omega 1 defined by block of f of alpha is the sup of f on the alpha block of f. So in these Martin type games, two players, by playing real good code, essentially good codes, are actually producing these auxiliary functions of the form omega times epsilon into omega 1. But the function that we're really concerned with is not the omega times epsilon sequence, but rather the block of these sequence. And so the point is that in Martin type games, as always, by AD, one of the two players has a winning strategy. But the important point is that the losing player, for the losing player, you can find a certain club C so that as long as the losing player plays into that club, you actually dominate all possible moves that the winning strategy can produce at a for its particular term of its auxiliary function. So doing it this way, since the losing player's move always dominates the winning player's possible response, when you take the block of it, it's actually player 2 that completely controls the identity of the block of f. So although the person who had the winning strategy controlled the property of the intended object, block f, it's actually player 2 that determined what block f will actually be. And using this sort of idea with these Martin type games, we can prove the following almost everywhere uniformization in the good code. So, okay, always have
William, could I just ask, this epsilon here is supposed to be less than or equal to omega 1, or?
It's less than or equal to omega 1.
Okay, okay.
And it could be omega 1 itself.
Okay.
Okay, so okay, in the back, always have a fixed good coding system. if you have a relation on omega 1 to the epsilon of the correct type cross R, then there is a club C and some Lipschitz function coming from some player 2 winning strategy, so that for any good code E, which codes a function from omega times epsilon into C, so that the intended function, the block of the function coded by E, does belong to the domain of R, then the Lipschitz function C of E is a real which is associated to the block of decode E with respect to the relation R. So you can kind of uniformize as long, but only if you have only in the code for the function that you're intending to uniformize for. Okay, so this uniformization will be useful for coding representatives of the ultra power by reals. So fix a function from omega 1 to the epsilon into omega 1. And we're going to, so let's define the natural relation attempting to code phi. So R of F and W hold if and only if the order type of W is the value of phi on F. Now, applying the good code uniformization, we can find a club subset of omega 1 and a Lipschitz function C with the property that for all good codes E for a function, for an omega times epsilon function passing through C, the order type of the Lipschitz function C of E is phi of the block of the sequence coded by E. So now, since every Lipschitz function can be coded by a real, so let rho be a real that codes this Lipschitz function, and pick a club code Z for a subclub of that club C above. And so in the sense that we, in the above sense, this pair rho Z kind of naturally codes the function phi, at least almost everywhere, right, on C to the epsilon. Okay, so let me abstract this definition. So we'll call a pair rho Z a epsilon function code if and only if Z codes a club, E codes a, and for all good code passing for an omega times epsilon sequence passing through the club coded by Z, the rho Lipschitz function applied to E is an ordinal. So this is attempting that thing should be the value of some function on the function coded by E. And 3 is kind of the most important well-definedness condition. For E0, E1, both good codes, for a function passing through the required club CZ, if the block of the function coded by E0 is equal to the block of the function coded by E1, then the order type of the rho Lipschitz function applied to E0 is equal to the order type of the rho Lipschitz function applied to E1. So in other words, this is kind of well-defined, independent of the good code for any possible auxiliary function for the intended function, which is the block of the decode of E. So so when rho Z is a epsilon function code, it allows us to define a function phi of rho Z on some club D to the epsilon into omega 1 by letting phi rho of Z of F equals alpha if and only if for every single E which passes through the club CZ, which codes an auxiliary function generating F, alpha is the order type of the rho Lipschitz function applied to E. So note that condition 3 is important. It makes this definition well-defined, right? It said it's independent of any E that I choose that codes an auxiliary function generating F. Okay. Now, you can check that when epsilon is less than omega 1, the collection of epsilon function codes is a pi12 set. And when and the omega 1 function codes is a pi13 set of reals. So this is kind of the main difficulty that comes between studying the short partition ultrafilters and the ultra power by the strong partition measure. So this difference in complexity comes from the fact that when epsilon is less than omega-1, the collection of good codes is a pi1-1 set of reals, but when epsilon is omega-1, the collection of good codes must be complicated. It has to be pi1, pi1-2, even pi1-2 complete. Okay. So by that little argument I gave like 2 slides earlier involving the good code uniformization, we know that every function phi from omega-1 to the epsilon into omega-1, you can find a pair rho z, which is an epsilon function code, so that phi of rho z is almost equal to the function phi according to the epsilon partition measure. Now, rho z is just a real, so phi of rho z belongs to the inner model L of R. Therefore, the ultra power of omega-1 by the epsilon partition measure as computed in the real world satisfying determinacy, it's the same as if you computed this, ultra power inside of L of R. Kekris showed that under AD, L of R is always a model of dependent choice, right? So therefore, this ultra power is actually always well-founded. So what we've shown is that these ultra powers are always well-ordering, even if the outside universe doesn't satisfy dependent choice. We just need that the inner model L of R always satisfies dependent choice. Okay, so this addresses the question of showing under AD alone why these ultra powers are actually well-orderings. So now, in the natural way, let's code the ultra power relation as a relation on these function codes. So say that rho 0 d0 is less than rho 1 c1, if and only if, first of all, both of these pairs have to be epsilon function codes, and there exists a real z which codes some club cz, which is a subclub of the z0 club and the z1 club. And for every single good code E, if E is codes an omega times epsilon function passing through the club coded by Z, then the order type of the rho 0 Lipschitz function applied to E is strictly less than the order type of the rho 1 Lipschitz function applied to E. So remember, these latter 2 order types are supposed to represent the value of the function coded by rho Z0 and rho Z1. Okay, so we have that when epsilon is strictly less than omega-1, the epsilon function code comparison relation is a well-founded sigma 1,3 relation, which corresponds exactly to the ultra power of omega-1 by the epsilon partition measure. And the omega-1 function code comparison relation is a well-founded sigma 1,4 relation, which corresponds exactly to the ultra power of omega-1 by the strong partition measure. Again, in condition 2, there is this universal quantification over the good codes, right? And this is why one of them is more complicated than the other one. Okay, so since the epsilon function code comparison relation, the function comparison relation is sigma 1,3, and hence omega sub omega Suslin by that result of Martin when epsilon is strictly less than omega-1, the CUNY-Martin theorem then states that implies that the ultra power of omega-1 by the epsilon partition measure is strictly less than omega sub omega plus 1. And we actually get a little bit more using, again, the fact that the collection of good codes for when epsilon is less than omega-1 is pi1,1, we can combine certain definability argument along with Steele's, Steele's result that there exist these, omega-1 Suslin bounded pre-well ordering to essentially get for free that, in fact, the ultra power of delta 1,3 by the epsilon partition measure is delta 1,3. So delta 1,3 is the fixed point of these short partition measures, right? And with this result, this is fairly complete answer to Goldberg's question when epsilon is less than omega 1. Okay, so for the rest of this talk, we'll be dealing with the strong partition, the ultra power by the strong partition measure, which is much more complicated. But okay, what do we get from our kind of very coarse comparison relation? So when epsilon, so the omega 1 function code comparison relation is sigma 1, 4, and by the result of Moshkovakis, it is omega sub omega plus 1 Suslin and well-founded. So by the CUNY-Martin theorem, the ultra power of omega 1 by the strong partition measure is less than omega sub omega plus 2, which is delta 1, 4. So we want to do better than just this. So the problem is that the high complexity comes from, in all our definitions, there is a certain universal quantification over the good code for functions from omega 1 to omega 1. And this is necessarily a pi 1, 2 complete set. So such quantifications will always yield very high complexity. So to improve the upper bound, we need to somehow avoid these types of universal quantifications. So it'll turn out that continuity properties for functions from from the strong partition space into omega 1 will be useful. And in the last talk, we showed that continuity. The continuity property follows from the strong partition property and something I call the almost everywhere short length club uniformization on omega 1. So we should probably go back at this point and address why this type of club uniformization is even true under AD. So to prove club uniformization, we need to kind of strengthen Martin's good coding system to include a coding of bounded sequences which interact with the good coding system in some very strict, under strict definability conditions. So a good coding family, first of all, must have a good coding system for functions from omega 1 to omega 1 in the sense of Martin from earlier. But in addition, it has a set of reals, BS, and a decoding function, seq, which is a surjection of BS onto the collection of bounded sequences of countable ordinals. There is a continuous function merge from R cross R into omega 1. And what it does is that whenever you give me a code U for a bounded sequence and a good code E for a full-length sequence, the merge of U into E will always be a good code for full-length sequence, but what it codes is the sequence where the full-length sequence where the bounded sequence coded by U will override a initial segment of the full-length sequence coded by E. And we need one other definability condition. If you have any bounded subset of omega 1 and any function passing through X, the collection of BS codes U so that the sequence coded by U passes through X and the block of the sequence coded by U is this L is a Borel set. So in other words, the collection of auxiliary functions passing through X coding L is Borel. Okay, so we can show that there are good coding families for omega 1. And what you do is first you take any good coding system for omega 1, and we will add some things to it to turn it into a good coding family. So so you can, for instance, let BS consist of those real U so that the 0th coordinate of U codes a well ordering whose intention is to code the length of the sequence, and the 1 coordinate of U codes a real so that so that in its section, it's going to code a sequence whose length is the order type of the 0th coordinate of U, the 0th coordinate of U. So there are many, any natural way you can do this. So now the new good coding family will consist of pairs UE, where E is an object that's related to the original good coding system, and U will be some real that's trying to imitate the definition of imitate being BS, as I described just before. So it has to kind of imitate being a bounded sequence, because if it really was a bounded sequence, it would be saying that something really is a bounded sequence will make certain things pi11 and will destroy the definability conditions that are required to be a good coding system. Okay. So now, so let me remind you again what the club uniformization principle said from last time. So almost everywhere short-length club uniformization holds that omega-1 means that for every relation on omega-1 to the less than omega-1 cross club subset of omega-1, which is subset downward closed, there is a club C, so that the relation can be uniformized on C to the less than omega-1. So using the good coding family for omega-1, we can give a new proof that omega-1 satisfies the almost everywhere short-length club uniformization principle. And in fact, this proof uses only definable boundedness arguments, essentially, arguments only involving the point class. And I mentioned last time that the original proof of this for omega-1 uses category arguments and generic coding functions, which are very specific to omega-1 and don't really generalize. But now with the good coding family, so we can show that most of the other well-known strong partition cardinals of AD have good coding families, right? So these include all the odd projective ordinal, delta 2,1, and delta A, which is the sigma 1 stable ordinal of LAR for any A subset of R. And in fact, for delta 2,1 and delta A, these good coding systems come from the uniform coding lemma Moskvakis, involving the recursion theorem, and in this case, the merge function actually comes from the some instance of the SMN function, that come along with these recursion theorems. And in some sense, the good coding family for like delta A and delta 2,1 are a lot more natural than the good coding family for omega-1, in the sense that the merge function is a lot more well behaved. Okay, so but once these strong partition cardinals have good coding families, they will satisfy the almost everywhere short-length club uniformization, and they'll possess many of the familiar properties of omega-1, including these almost everywhere continuity properties. Okay. So this is a good so we talked about the good coding family and how they're used to get the club uniformization principle. So they'll come up again when we have to code the ultra power. But from last time, we saw that one of the consequences of the almost everywhere club uniformization principle are these continuity properties. And these continuity properties seem to be very useful for simplifying the coding of the ultra power, right? So continuity said that for any function phi, there is a bounded segment of f, so that which completely determines the value of the function. Now, the problem with the original continuity property is that recognizing a bounded sequence is a continuity point is it seems to be very complicated. You need to say something like some bounded sequence is a continuity point if for every full-length function extending that bounded sequence, the function is constant. But that seems to require a universal quantification over all the good codes that extend a bounded sequence, and that's going to push the complexity up too high. But last time we saw that with the club uniformization principle, we actually get this finer form of continuity. Let me state it in this form so we'll use it in the following form. For any function phi, there is a club C so that for any bounded sequence sigma passing through C, if you are able to find a full length sequence G so that phi of sigma concatenated by G is less than the sup of sigma, then I will know for sure that sigma is a continuity point for phi, at least relative to that club phi, right? With this continuity property, let me, using this continuity property, I'm going to motivate the notion of a pseudo-continuity point. So a pseudo-continuity point is basically the coded version of the sigma from the above theorem. So we say that U is a pseudo-continuity point for a triple rho z E. So at the moment, I haven't put any conditions on rho z E yet, but it's supposed to code some kind of function. So you're a pseudo-continuity point if U codes the sequence passing through the club coded by Z, and the sup of the sequence coded by U is less than the function coded by E evaluated at the length of the sequence coded by U. And when you apply the Rho-Lipschitz function to the merge of U into E, this is a well-ordering whose order type is less than the sup of the sequence coded by U. So you can check that essentially I have just rewritten the notion of being a continuity point from the theorem as a relation on BS. You can check that being a pseudo-continuity point is a pi11 relation. Okay, so what are the triples rho z E that we're going to be interested in? So we say that rho z E is a pseudo-function code if and only if, okay, Z codes a club, E codes a full-length sequence passing through that club. For any real U and U bar, let's say that U is a pseudo-continuity point in the sense of the previous slide. U and U bar both code sequences passing through the club coded by Z. The block of the sequence coded by U is an initial segment of the block of the sequence coded by U bar. Then the Rho-Lipschitz function applied to the merge of U into E and the Rho-Lipschitz function applied to the merge of U bar into E are both well-ordered encoding the same countable ordinal. So the idea is that U is supposed to be U is a pseudo-continuity point, right? So this last condition here said that if you think of rho z, the Rho-Lipschitz function as defining a function into omega 1, then U really does act like what we think a continuity point should act. That's kind of the intuition for 3. Okay. Now, if you can check that being a pseudo function code is pi12. So this looks like progress now, right? Remember the omega function code from before was a pi13 set, but we have defined some triple whose intention is to code some kind of function as a pi12 set. Unfortunately, you can't use the pseudo function code. There's some problems, but okay, we'll come back to that in a moment. Okay, so if rho z E is a pseudo function code, the intuition is that it's supposed to code a function, but rho z E will code a partial function, which we call phi of rho z E. But it really is a truly partial function. So we say that a function f belongs to the domain of phi of rho z E. Intuitively, if and only if there is an initial segment of f, which is a pseudo-continuity point. So more precisely, this means that there is a U, so that U codes a sequence passing through the club of Z. U is a pseudo-continuity point for the triple rho z E. The sup of the sequence coded by U is less than the sequence coded by E evaluated at the sup of the sequence coded by U, and the block of the sequence coded by U is an initial segment of F. So when all of this happens, then we will define phi of rho ZE of F to be the order type of the rho Lipschitz function applied to the merge of U into E. And again, this is well defined because of that this condition 3 from before that says that if U is a pseudo-continuity point, it in some sense really does act like a continuity point. Okay, so now the most important point about this definition is that in order to compute the value phi rho ZE of F, I never used a good code for F. So that's very important. Instead of using a good code for F, all I did was search for a BS code for an initial segment of F, which is a pseudo-continuity point. Then I took that BS code and I merged it into the one single fixed good, the good code E was fixed at the very beginning, right? So I merged this one, the BS code for a pseudo-continuity point into the fixed good code E, and then asked what happens under the Lipschitz function, and that gives me the value of the function. So I never needed to have a good code for F to compute the value of this function. Okay. So now I mentioned there's a problem with the pseudo function code. So being a pseudo function code, so the problem is that if rho ZE is a pseudo function code, the domain of phi of rho ZE may not be defined on a very large set, namely that it may not be defined on a set which is large according to the strong partition measure. So let's call a triple rho ZE a true pseudo function code if the domain of phi of rho ZE is actually large according to the strong partition measure. Okay, so these are kind of so these true pseudo function code will define representatives of the ultra power. Okay, so now let's define the natural comparison relation for pseudo function code. So remember, for pseudo function code, the idea is to get the value of a function by using the bounded segments, which are pseudo-continuity points. So let's compare pseudo-function codes by comparing behaviors at these continuity points. So say that rho ZE0 is less than rho ZE1 if and only if there is a Z coding a club, which is a subclub of both the Z0 and the Z1 club, so that, so the main idea of 2 is that there is some U code for a bounded sequence passing through the Z club, so that so that U is essentially a pseudo continuity point for both rho ZE1 and rho ZE0. When you look at the order type of the rho 0 Lipschitz function applied to the merge of U into E0, it is strictly less than the order type of the rho 1 Lipschitz function applied to the merge of U into E1. So remember, these two order types here are essentially the values of phi rho ZE0 and phi of rho ZE1, right? So naturally, this is kind of comparing these two functions by just checking out what happens at the pseudo-continuity points. Okay. You can check that the pseudo function code comparison relation is sigma 1,3, so that looks really good for applying the CUNY-Martin theorem. But there is a problem though. In order to apply the CUNY-Martin theorem, you need to know the relation is a well-founded relation. So when you restrict the pseudo function code comparison relation to the collection of all pseudo function codes, I'm not able to show that it is a well-founded relation. And the main problem is that there are some pseudo function codes which are not defined, whose domain is not a large set according to the strong partition measure. And it seems that in order to establish well-foundedness, I need to restrict the pseudo function code comparison relation to those true pseudo function codes whose domain are large according to the strong partition measure. But so later we will see that the collection of true pseudo function code is actually a fairly simple set. But a priori, being a true pseudo function code means that your domain is large according to the strong partition measure, and at the very least, you will need a universal quantification over good codes in order to state that, right? And this will push the complexity beyond what we can handle. But what we do have is that if you have a set A, which is a sigma 1, 3 subset of the true pseudo-function codes, and then the restriction of the pseudo-function comparison relation to A will be a sigma 1, 3 well-founded relation, which corresponds exactly to so that its order type will correspond to the corresponding subset of the ultra power by the strong partition measure, and this corresponding subset of the ultra power will have order type strictly less than delta 1,3 by the CUNY-Martin theorem. This result is still useful for getting local bounds. If you pick one single function psi from the strong partition space into omega 1, so from earlier in the talk, we know that such functions have a pair rho star z star, which is a omega 1 function code in the strongest, nicest sense from earlier in that talk. Pick any E star, which is a good code passing through the club coded by Z star. Rho VE star is in fact a true pseudo function coding psi, but because rho Z star is a omega 1 function code, is actually much nicer than just being a true pseudo function code. Now let A be the pseudo function code rho Z E, so that roughly whenever U is a pseudo continuity point for rho star D star E star, U will also be a pseudo function code for rho Z E. So the important point is that since rho star Z star is one of these really nice omega 1 function codes, it has lots and lots of pseudo continuity points, right? They're like dense in everything passing through the Z star club, and therefore by the definition of A, we have that every element of A is a true pseudo function code, and you can check that A happens to be a pi12 subset of true pseudo function code. So using this previous theorem down here, we can now conclude that the ultra power by the strong partition measure strictly below the function psi has order type strictly less than delta 1,3. And if you range over all the representative psi, you will be able to show that the ultra power of omega 1 by the strong partition measure is less than or equal to delta 1,3. So for the rest of the talk, we'll be trying to improve that and get strictly below delta 1,3. But what is useful about the argument we've done so far is that essentially nothing I've done here is truly unique to omega 1. If you use Jackson's description analysis and get a good coding system for the higher objective ordinals, everything I've done so far would allow you to show that the ultra power of delta 1 2m plus 1 by a strong partition measure is less than or equal to delta 1 2m plus 3, which is the next strong partition cardinal after delta 1 2m plus 1. What I'll show next, that the ultra power by omega 1 by a strong partition measure is strictly than delta 1,3, is specific to omega 1 because it uses certain hereditarily countable sets. Okay, so the rest of the talk will be to get that bound strictly below delta 1,3. So for this, we'll need to talk about the linearly iterable structures. So in the context of this talk, a pre-mouth will be a structure of the form L of x mu bar, delta bar, mu bar, kappa, and U, where x will be some real. Lx of mu bar is a model of CFC without the power set axiom, and kappa is the largest cardinal. Mu bar will be an internal sequence of normal ultrafilters, so that its sequence of critical point forms a discontinuous sequence swooping up to that largest cardinal kappa, and U is a kind of is an external normal measure on that top cardinal kappa. Okay, so there's a number of different types of linear iterations you can do with models of this kind, but we'll just need the following simple type of linear iteration. So let L be a sequence of ordinal. So let me define what it means to iterate with instruction L.
William, can I just ask, these premise are supposed to be set size structures, or?
Oh, okay, yes. Okay, so in fact, I will probably want it to be countable. Yeah, so it should be like L sub alpha or
something. Okay,
yeah,
all right. Good.
Good point. So what does it mean to iterate with instruction L? So suppose epsilon is less than L, and for every alpha less than epsilon, I have defined the iteration for L restricted alpha. So how do I get the next step? So let N0 be the direct limit of all the previous M restricted to alpha. So next, take the top external measure of N0 and take one ultra power by that top measure and call that model N1. Now, starting from N1, look at every step, look at the measure indexed by epsilon and iterate the epsilon index measure each time, well, at least L of epsilon many times. And then take the direct limit of everything. And this will give you M restricted, sup L restricted to epsilon. And then finally, in the end, define ML to be the direct limit of M of L restricted to epsilon for every epsilon less than length of L. Okay, so but let me just point out what is the point of this ultra power by the top external measure. So at a certain point along your iteration, it might be the case that N0 doesn't have a measure index at epsilon. This could happen if epsilon ends up being that top cardinal kappa, right? So the point of taking that one ultra power is to move up the top cardinal a little bit so that now you will have an epsilon, a measure index at epsilon, and then you can continue with the iteration like I described. That's the point of the one ultra power at the top. Okay, so now we will call the structure M a mouse if all linear iterations of the form I described are well-founded. Let mouse be the set of reals coding countable mouse. Mouse will be a pi12 set of reals. And okay, so by sigma 11 boundedness and probably other ways to see this, if M is a countable mouse, then you can find a club C so that for every L passing through this club, if I iterate M using L itself as an instruction, L will be the M sub L's own sequence of critical points. So in other words, there is a club, so for every L through this club, there is a way for me to iterate the model to align up the critical point with the sequence L itself. And let me just remind you this result from last time to show why these mouse exist. So last time we showed that using just the club uniformization principle, for every real X, for mu almost all F, the model LX mu1 F, mu1 is the club measure. This model has an inner model containing X where the true omega 1 is a measurable cardinal and a limit of a discontinuous sequence of measurable cardinals. Using this result, and you know, we're working under AD, right? So you can use other consistency results, but to show that for any real X, there is a countable mouse containing X. Okay. So now we're finally ready to show the collection of true pseudo-function code is actually delta 1,3. And for the Kuhn-Martin theorem, in fact, I only needed to be sigma 1,3. So let me tell you what the formula is. So I claim that rho ZE is a true pseudo-function code if and only if there exists a countable mouse M containing the triple rho ZE so that M satisfies the following statement. So inside of M, rho ZE is a pseudo-function code, and there is an alpha less than the top cardinal, so that if I collapse the alpha term of the measure sequence to omega, in that forcing extension, there is a U, which is a codes a bounded sequence. U is a pseudo-continuity point for the triple, and the block of the sequence coded by U is the alpha initial segment of the sequence of critical points. Okay. Now, since mouse is pi12 and satisfaction, so the satisfaction relation is delta 1, 1, you can check that this is a sigma 1, 3 relation. So let me just sketch why the right-hand side of this expression implies rho z e is a true pseudo-function code. So remember, being a true pseudo-function code means that for almost all f, there is an initial segment of f, which is a pseudo-continuity point. Okay, so assume the right-hand side. So fix a countable mouse m. So by the result, this result earlier, there is a club C so that I can iterate for any sequence through C. I can iterate M in such a way to align up the critical point with that sequence through C. So fix an arbitrary F from omega 1 into this club. Now let MF be the iteration with instruction F, and we showed by the previous fact that if you iterate M with instruction F itself becomes the sequence of critical points. So by elementarity, MF satisfies the statement above, meaning that there is some alpha less than its top cardinal, which less than omega 1, so that if you collapse f of alpha to omega, in that forcing extension, you have a BS code for f restricted alpha, which is a pseudo-continuity point relative to rho z e. Okay, so now M sub f is a model of choice. V is the background universe is a model of AD, and since alpha is less than omega 1 of V, this collapse forcing is countable from the point of view of the background universe V, since omega 1 V is inaccessible to the reals. So therefore, in the real universe, you can pick a generic G, and then if you look at MF of G by the forcing statement, there is some alpha, there is some U, which is a real U, which is BS code. The important point that since the generic belongs to the real world, this U actually belongs to the real world too. So U codes F restricted to alpha, and U is a pseudo-continuity point relative to rho z E. Now, omega 1 of V is a subset of MF of G. Being a pseudo-continuity point is pi1, 1. Being a pseudo-function code is pi1, 2. So all the statements in condition 4 is by Schoenfeld absoluteness. All the statements about U by Schoenfeld absoluteness remain true in the real universe V, and therefore in the real universe U is a pseudo continuity point for rho z E. U codes an initial segment of F. And therefore, by definition, F belongs to the domain of phi of rho z E. And so F was a totally arbitrary element of that club C. So this shows that the domain of rho z E is large according to the strong partition measure. And that's the definition of rho z E being a true pseudo-function code. So this is one half of the argument that being a true pseudo-function code is sigma 1, 3. So that's all I'm going to say about this proof. Okay, so now that we know that the true pseudo-function code is sigma 1, 3, by that earlier result, we have that the pseudo-function code comparison relation restricted to the collection of true pseudo-function code is sigma 1, 3. It is well-founded because the corresponding ultra power is the entire ultra power. And therefore, by that earlier result, applying the Kunin-Martin theorem to the sigma 1, 3 well-founded relation, we know that the ultra power of omega 1 by the strong partition measure is strictly less than omega sub omega plus 1, which is equal to delta 1, 3. And this answers Goldberg's question even at the strong partition, the strong partition measure. Now, remember, for epsilon less than omega 1, we showed that delta 1, 3 was even a fixed point of these ultra powers. So I don't know at this moment whether the ultra power of delta 1, 3 by the strong partition measure is delta 1, 3. So probably right? So if the intuition to Goldberg's question is that delta 1,3 cannot be reached by ultra-powered by partition measured less than delta 1,3, probably the answer to this question is it captured that intuition probably better than the original form of Goldberg's question. So unfortunately, the problem is that, as always, the collection of good codes is pi12, so I can't use this Steele pre-well ordering type argument to essentially get for free from the previous theorem the answer to this question. I actually do need to, it seems that in order to answer this question, you do need to analyze the ultra power of each omega n by the strong partition measure. But the problem is that once you get beyond omega 1, these functions start exhibiting new behavior. For instance, the function psi from the strong partition space into omega 2 defined by psi of f is the ultra power of f by the club measure. This is an ultra power map, right? So it doesn't have any kind of continuity property that we recognize, or at least it seems to be useful. So probably to answer this type of question, we'll need to do a combinatorial analysis of these type of functions, try to find what type of useful almost everywhere behavior these things can have, and then come up with some kind of good coding, coding mechanism that will interact well with this behavior in order to code these ultra powers in a sigma 1,3 way, in some sigma 1,3 way. This is the state of the knowledge of these ultra powers at the moment. Thanks for listening.
Thank you. Very interesting talk. Can I just ask? Let me just. Okay, totally naive question. Like, if you look at epsilon less than omega 1, at the sequence of the say ultra powers of omega 1 by these partition measures, do you know anything? Are they increasing or like weakly increasing?
Oh, you mean for epsilon as you increase the epsilon,
yes.
Like epsilon 0 less than epsilon 1?
Mm-hmm.
So if you can embed each one of these into the other one in some kind of natural way. So they're always, in fact, strictly increasing.
Mm-hmm. And you know that they are always cardinals, right?
No. So because all of them we showed. We showed that for every epsilon greater than omega and less than or equal to omega 1, they're between omega sub omega and omega sub omega plus 1, right? So there's no cardinal.
Oh, okay.
Right.
Okay.
Is the sequence discontinuous everywhere?
Well, certainly it's discontinuous at omega, right? Because all right, so all the finite ones are omega sub m plus 1, and you can actually show
they
that
all have uncountable cofinality.
So all of them have uncountable cofinality. For epsilon less than omega 1, we know that their cofinality is omega 2. For the strong partition property, once you have this result here, we know that the ultra power by omega 1 by the strong partition measure also has cofinality omega 2, but it's not clear to me at all what the omega 2 cofinal sequence is.
So is there, it's interesting they all have cofinality omega 2. Is there a more direct proof that shows that, since it's also the same as all the...
Yeah, well, so that's kind of the problem for the ultra power by the strong partition measure. By the very fact that it's less than delta 1,3, it's why we know it has an omega 2 cofinal sequence. For epsilon less than omega 1, you can actually directly create the omega 2 cofinal sequence. They're in some sense defined by when epsilon is less than omega 1, you can take the soup of the sequence, right? And these soup things kind of define the omega 2 cofinal sequence. But this only works when epsilon is less than omega 1. Yeah, does that?
Are they cardinals in HOD? Like how big of inner models are these things cardinals in?
I actually don't know. Oh no, well the cofinal sequence. Well, okay, the cofinal sequence is ordinal definable, or at least for epsilon less than omega 1.
So they're singular in Hod.
Yes, yes.
Like the omega n's, I guess.
Uh-huh.
Thank you.
Mm-hmm. Yeah, I hope this was, I don't even remember what, yeah, I guess what question you asked, Jack.
Oh, well, you gave me too much credit. Like you act like I had the correct intuition for the answer to the question when really I asked the opposite question and you refuted whatever
okay.
in my mind.
I see. I think when Jackson originally thought about this, we thought it could probably go very far, right? But
any further questions?
I've got a quick one.
Mm-hmm.
So many slides back, you mentioned this ordinal delta sub A for a set of reals. The definition of that went by a bit quickly. Could you remind me what that was?
Let me see if I can find it. Okay. So it is the So delta sub A, it's called the sigma 1 stable ordinal of LAR. So it is the least ordinal delta, so that L delta A of R is a sigma 1 elementary substructure of LAR in the language where there's a predicate for each real and the collection of reals.
Oh, okay, cool.
And it turns out in L of R, delta empty set is delta 2, 1.
Okay.
Mm-hmm.
Is for that last fact you mentioned, is that obvious, or is there a source for that?
Okay, so I guess I showed that the thing is a good coding family, but the fact that these are strong partition cardinals is a result of Kekker's, Kleinberg, Moskvakis, Wooden, some paper about singular measures or something. I can't remember the title exactly, but it involves the uniform coding system and the recursion theorem and the SMN theorem, these type of things.
Okay, cool. Thanks.
Okay. Any more questions for William? Doesn't seem to be the case. Okay, well, thank you so much for these two talks. That was really interesting. Thanks a lot.
Thank you.
All right. Have a good weekend, everybody.
Bye.